Okay, so there are many other things that we could have said about light front quantization. We're going to stop here. It is not our main interest, but I would encourage you to read further if you're interested and go look on the internet. There are plenty of very good sources. Okay, now what I would um, like to do now is to discuss what we're really interested in, which is radial quantization. And I'm going to start off by sort of just indicating some differences between quantum field theory and conformal field theory. So let's first of all think in quantum field theory, and let's think about the kinds of things that we're interested in measuring in quantum field theory. So you may have remembered just a few years ago, there was a very big deal about the Higgs boson being discovered at the LHC. And one of the things that they measured was the mass of the Higgs boson. So the mass of a particle is always equal to the energy squared minus P dot P. So if you wanted to measure the mass of a particle, when you detect the particle, you'll measure its energy and its momenta, and then you can read off what the mass of the particle is. Um, when you have a beam, they will talk about the center of mass, energy of the beam. Um, when you talk about a particle being detected in a detector, you can usually see with what momentum the particle was detected, and so on. So the kind of observables that you're interested in, so observables, kinds of things that you're interested in is the energy that's associated to the Hamiltonian. You would maybe also have momenta and so on. Um, then you would calculate S matrix elements. So we would have an S matrix, and we could look at S matrix elements for particles that have some definite uh, energy and momentum. So one of the things that was central in quantum field theory was the Hamiltonian. And of course, we know that the Hamiltonian is closely related to an equal time quantization. So we foliated space-time by collecting all events that are at the same time. Those all sit on one leaf inside the quantization, and the Hamiltonian generates transformations between the different leaves of the foliation. It lets you go from one equal time surface to another equal time surface. So that's just a few comments about quantum field theory. Now let's think about conformal field theory. Well, the first thing that you know is the above picture certainly has to be modified. Why is that? Well, we know there's no S matrix. That's what Coleman and Mandula taught us. There's no S matrix, so then what kinds of observables do we study? Well, we would study things like a two-point function of operators. And if we pick the operators correctly, these two-point functions take the form of a power law. And I said if we pick these operators correctly or we pick nice operators, what I mean is these operators have a scaling dimension, have a scaling dimension. So we're not interested in the energy of a state or an operator. We're interested in its scaling dimension. And the scaling dimension is measured by the dilatation operator D. Now, you might wonder, you might think, why don't we look for a basis in which operators have a good scaling dimension D and they have a good um, energy H. Well, one of the things that you will remember is that we calculated the commutator between D and P mu, and I don't remember the signs and so on, but this came out proportional to P mu. There's maybe an I, it's a plus I or a minus I don't remember. But the point is, if you calculate the commutator of the dilatation operator with the Hamiltonian, this is proportional to the Hamiltonian again. So if you're dealing with any state with a non-zero energy, the commutator of the dilatation operator and the Hamiltonian do not commute. So you cannot find operators that have both a good scaling dimension and a good energy. So we now decide that we're going to study these scaling dimensions. And the scaling dimensions are super important because the scaling dimension delta determines the powers of the power laws. So in the CFT, what do we observe? We observe correlators. What do we want to measure? We want to measure the power laws. So we want to measure the power of the power laws, and that equivalently means we want to measure the dimension of the corresponding operators. So the role that was played by the Hamiltonian is now being played by the dilatation operator. So what you might wonder is, we had this equal time quantization, and the Hamiltonian defined a time evolution operator that went between the different slices of the equal time quantization. Is there a quantization in the conformal field theory so that the finite transformation generated by the dilatation operator takes us between different slices of this quantization? And the answer is yes, and that is precisely what we mean by radial quantization. So in radial quantization, we evolve between the different leaves in the radial quantization using the dilatation operator, and this replaces the statement that we evolve between the different leaves in the equal time quantization using the Hamiltonian. So this was just a very rough discussion just to give you some intuitive feeling for what radial quantization is all about. We're going to start actually defining radial quantization carefully in a moment.